Welcome to the last video of this double section. We're going to talk about annuities and give some examples. So remember, if we just input money once and let it grow with interest, that's compound interest. If we regularly put in money, that's an annuity, a savings annuity, like a retirement account. So let's say that we have a traditional individual retirement account, otherwise known as an IRA. The special time of a retirement account where the money that you invest is exempt from income taxes until you withdraw it. Okay, so you can put in money pre-tax. Then it's taxed at the end when you take it out. So if you deposit $100 each month into an IRA earning 6% interest, similar to our little example before, how much are you going to have after 20 years? Well, let's use the formula. We know that the amount is D times 1 plus R over K to the KT. 1 plus R over K, KT minus 1. And that's all divided by R over K. So it's a little messy, but let's just find everything. D is how much we're putting in every pay period. Usually it's going to be the same as the compounding frequency. All right, so D is just going to be, we're putting in $100 each month. R is our APR, 6% as a decimal. K is how often it's compounding. That's 12 every month. And T is how many years go by. 20 years. Now we just plug it all in. Again, you can simplify it along the way, but I think a lot of times it's easier to just kind of simplify it all at once. So we get 100 times 1 plus 0.06 divided into 12 pieces. There are 12 months in a year, 20 years going by. We're subtracting 1 before we multiply it by 100. The whole thing gets divided by R over K, which again is the 6% interest divided into 12 pieces. If you do want to simplify it earlier before going on, feel free. Or you can type it in from now. Be very careful. This is where things get tricky to type things in. So that can be an advantage to doing it in smaller pieces. We have a whole fraction. I'm going to give us an extra parentheses so that we make sure the whole thing gets divided. It's going to be that 100 times, we have 2 parentheses now, so let's make sure to include 2 parentheses here. 1 plus R over K, end parentheses, raised to the K times T. Remember, I have to use parentheses here so that the whole exponent stays there. Minus 1. And then we end the parenthesis for the D part. And we end the parenthesis for the fraction so that when we hit the divided by sign, the whole thing is there. We'll have R over K. So the calculator is the hardest part of this. All right. And then we double check and say, okay, we have an extra set of parentheses. But other than that extra set of parentheses, does it look about right? Extra set of parentheses up here too, but looks about right. Does the number make sense? Well, it's kind of hard to see whether the number makes sense now. Let's write it down and go from there. 46,204.09 if we round to the nearest cent. Okay, so we're depositing $100 every month for 12 years. $100 every month for, 20 years. So we put in $24,000 total over those 20 years. We put in 24K. It grew to 46K. This sounds believable. So there we go. That's our answer. Great. Let's do some more problems. Let's make things a little bit more complicated. Let's say when we retire, we want to be a millionaire. We want to have $1 million, and then we can really just live on the interest. Mostly, you want to have $1 million in your account when you retire in 30 years. Let's go. Let's save aggressively. All right. Then your retirement account, let's say our retirement account earns 8% interest, which is, pretty believable, pretty standard. Again, a lot of times if you do invest in like the stock market, you'll, a lot of times gain between 7 and 10% every year, when the stock market is not what it is right now when I'm recording this video. But anyway, how much do you need to deposit every month if you want to meet your retirement goal? So we've got A is D times 1 plus R over K, the KT minus 1 all over KT. Messy, messy formula. Let's break it down and solve. So the amount, that's what we want. We want to have $1 million at the end. D, how much do you need to deposit each month? We don't know D. It's going to stay right there. Everything else we can fill in. What's our APR? About 8%. Getting split up into 12 months. Okay, it didn't specify how often it's compounded, but usually the compounding frequency is going to match our deposit stuff for these problems, our deposit frequency. And we want it to be 30 years from now. That's our T. Whoa, this is wrong. I wrote down the wrong fart. The wrong fart? The wrong part. Be R over K down here. R is 0.08, and that's getting split up into 12 pieces, approximately. So again, don't freak out. It looks scary. But notice that what we have is the exact same thing as this. When we multiply two things together, right, that's like multiplying the numerators and multiplying the denominators. They're the same thing. And this over here is just a number. Numbers can't hurt you, I think. I don't know. So let's find out what that number is. Because then what are we going to have? We're going to have 1 million is equal to D times that number, and we can just divide both sides by that number and get to our answer. So it looks scary, but let's just find it. Okay. So we need to find 1 plus R over K raised to the K times T minus 1. And this whole thing has to get divided by R over K. We're going to need parentheses so we can divide the whole thing. Whole thing's divided by R over K. So 1490. Again, let's make sure to include a lot of decimal places. Otherwise, we're going to run into some weird issues. 1490.3594. Now we just divide that 1490 over, and we have our D. So if we divide it over, it's 1 million divided by that number. We'll get about $670.98. Okay. Let's say we're making 70K a year. Making 70, well, you're not bringing home 70K a year. Let's say we're bringing home 4,500 per month. Then 670 divided by 4,500. How much of this of our take home is this? This is about 15% of our take home. We're making 70K a year. All right. And that's assuming your employer is not matching anything. Okay, so it's aggressive savings, but it's okay. And also, notice an assumption here. We're putting in the same every month. Usually, when you invest in retirement, you put in a percentage of your income, right? So hopefully you're not making the same salary every day for 30 years. Hopefully not, right? At least, hopefully it's keeping up with inflation. So again, the 670 that we're putting in today is going to be way harder than the 670 we're putting in 25 years from now or something. So again, we're still making some approximations. for these calculations, they'd get a little bit more complicated if we put in a percentage of our income all the time. But yeah, that's what we'd want to do. $670 every month if we wanted to be a millionaire when we retire. All right. Let me know if you have any. Well, there's still another example. This much every month. I'm wrapping up the video. There's another one. Okay, let's go. If you invest $100 each month into an account earning 3% interest compounded monthly, how long will it take to grow to 10K? Well, same formula. The amount is D times 1 plus R over K, KT minus 1, all over R over K. Just fill in what we know and solve for what we don't. So we want the account to grow to 10,000. We're putting in $100 every month. We get 1 plus R is 3%, which is basically 2 or 3% is basically inflation in normal years with a healthy economy. Divided into 12, it's compounded monthly. The 12 times T, we don't know what T is. Minus 1 all over, again, that 0.03 over 12. Remember that these are always going to match. The R over Ks will always match. Okay. So this is going to be, I mentioned the last one wasn't that bad to solve. This one's badder to solve. It's worse to solve. Let's find out what 0.03 over 12 is. Is this something nice? I think it is. Good. 0.0025. Okay. So this right here is 0.0025. And this over here is 1.0025. That'll make things a little bit nicer when we're moving things around. Okay. So let's multiply both sides of the equation by that 0.0025. That gets rid of our denominator. If we're solving an equation and it has fractions, hypothetically, let's pretend you don't like fractions. You can just multiply both sides of the equation by the denominator of the fraction. And then fractions, boom, they're gone. Okay. I don't want to do this in my head. I'll mess it up. 10,000 times this number is 25. That's nice. I like 25s. The 25 equals the same thing without, again, this is 1.0025, the 12t minus 1. Okay, we need to undo this multiplication, so we're going to divide both sides by 100. Well, I still like that left-hand side. That left-hand side's looking nice. That's 0.25 on the left-hand side. The right-hand side is 1.0025 to the 12t minus 1. Oh! Look at what we got here. We've got an exponential equation. We know how to solve exponential equations. What do we need to do? We need to get the exponential the exponential part by itself. And then we undo exponentials with logarithms. I love you, good old loggies. You can call them loggies if you're really good friends with your logarithms. But to get the exponential part by itself, we're subtracting one. We need to undo that subtraction with a plussing. Okay, that's 1.25 equals 1.0025 to the 12t. Let's undo it with a logarithm. I always use natural logs. Let's use a common log. Common log of the left-hand side equals the common log of the right-hand side. I'm going to leave the left-hand side alone because I don't want to round. But the right-hand side, that exponent comes all the way down. We get 12t times the log of this thing. Again, it looks kind of scary, but it's not that bad. Because what's happening to the t? We want the t by itself. T is getting multiplied by 12 and it's getting multiplied by this logarithm. We can undo that by dividing by the 12 and by dividing by that logarithm. And if we divide both sides by this, the logs cancel, the 12s cancel, and we're just left with t. Nice hot tea with no sugar or cream. Just regular old tea. There we go. Let's plug it into a calculator. Remember, you can't simplify this log. Logs are squirrely to simplify sometimes. We got the log of 0.25 divided by, I don't remember. Oh, it's 1.25 divided by 12 times the log of 1.0025. Let's double check. 1.25 divided by 12 times the log of 1.0025. About 7.447. About 7.5 years. How long it's going to take. Doesn't really round to 7.5 years, but it's a good way of interpreting this answer. All right. Or again, you could say, well, it's 7 years and then 0.447. How much is 0.447 in months? 5 months. So about 7 years and 5 months. Okay. And that's how we can calculate it. Let me know if you have any questions. Some of this stuff can get a little messy, but it's good practice for some math. Have a good one.